Okay, so good afternoon, everyone. Thank you for coming to our workshop for today. So it says workshop 18, but this is not our 18th workshop. We still have a few more to go. We're adjusting the order of our workshops because a majority of your professors have decided to do organic chemistry first and then save nuclear chemistry as kind of that last topic. So since it's easy, since a few of them are doing it, I think it will be more convenient to kind of stay in track with what you're doing in lecture. That'll be really helpful. So today we're going to start off with organic nomenclature, we'll also talk about constitutional isomers, how to calculate degrees of unsaturation, and then kind of determine what our different functional groups are. So we're going to go through that today. We're going to get lots of practice, hopefully, with naming our organic molecules. And we'll see what we can retain from everything we're going to learn today. So I said previously, for OChem, a bit of it is memorization, right? You need to know what your functional groups look like and memorize the common ones that you'll need to know. Obviously, there are lots of organic groups, functional groups that you can learn, right? Hundreds of them. But you really only want to focus on what you're shown in lecture, right? So what your professor focuses on are the functional groups you want to focus on, but I'm going to go through a few of the common ones. So one functional group that's really common is our carboxylic acid functional group, and we're going to represent this by having a carbon with a double bond to oxygen, and then it should also have an OH or hydroxide group, and then on the other side of the molecule we'll have an R group. So we're calling our R group any other amount of carbons or atoms attached to our species. So when we think about our functional group, we're saying that the carboxylic acid functional group is really our COOH group. So another way that we can write it is COOH, where we have kind of the rest of the molecule attached there, right? So that's our carboxylic acid functional group. We also have our ester functional group, and it's similar to our carboxylic acid, but now instead of having a hydrogen as an OH, now we're going to have another alkyl chain or carbon chain on the other side of our oxygen. So now we'll have two R groups. Remember that R just represents some chain of carbons. It can have a few other atoms present, but we're saying that the main functional group that we want to think of for ester is our COOR. So you may also see this written as COOR as your functional group. Right? What about our amide? So our amide is similar to a ester. However, now we're switching out our oxygen for a nitrogen-containing species. So since we still want our carbonyl, we still want our C double bond O, but now the carbon in our carbonyl C double bond O is bonded to a nitrogen, and nitrogen can have two R groups, right? So there should be another R group on the other side of our carbon. So when we think of an amide, the functional group that we're looking at here is this carbon nitrogen species. Sorry, and you may see this written as CONR2. Or we can have different numbers of R's, or we can have different R groups. They don't have to be the same, right? So R attached to our nitrogen can be different, and we can indicate that with our dashes. So that's our amide functional group. We also have a nitrile functional group where we have R with a single bond to carbon and then a triple bond to nitrogen. And you may see this written as CN, right? That will be our nitrile group, abbreviated. We also have aldehydes, where we have a carbonyl once again. So we have a carbon with an oxygen, and now we have a hydrogen. So we'll typify our aldehyde functional group with our CHO group. So now we have CHO. You may also see it written that way. And whenever you see me draw a squiggly line, that just means that there's more of the molecule that I'm ignoring. Right? So that's our aldehyde functional group. And our ketone functional group is similar, but now instead of having a hydrogen on one side of the carbon-oxygen double bond and the R on the other side, for our ketone, we'll have R's on both sides of our carbon-oxygen double bond, right? And they don't have to be the same R group, right? But our ketone is this entire motif here. And now for our alcohol, this one is probably the one that you're most familiar with, where we have an R, and our alcohol just needs to have an OH present to be considered an alcohol. We can also have an amine, where we have a nitrogen surrounded by 3 bonds and a lone pair. And these bonds can be hydrogens or other carbon chains, but as long as we have 3 bonds to nitrogen with a lone pair, each of these R's can be different, right? That would be our amine. Alkenes are carbon-carbon double bonds, and you'll see them as carbon bonded to another carbon, and then each carbon should be attached to 2 more substituents, which we'll just write as R. Our alkyne is our carbon-carbon triple bond, and then each carbon should only get 4 bonds, so that means that there must only be 1 R group on each carbon. Alkanes are the simplest one, where we have our carbon-carbon single bond, and we'll generally see 4 attachments to each carbon, right? So that's another functional group. We can also have our ether, where we have a central oxygen in between 2 carbons, right? So we'll call this R and R prime. That just means that we can have longer carbon chains. And then our halogens can be Rx, where X can be equal to fluorine, chlorine, bromine, or iodine, right? So the halogen functional group is present here. This is our ester, alkane, alkene, alkyne. I stopped highlighting. And then lastly, we have our nitro group. So this is going to be a nitrogen, right? There should be 1 oxygen that has a double bond to nitrogen. A nitrogen should have a positive formal charge, and then the other oxygen has a negative formal charge, and then this is attached to an R group as well. So this can be written as R and then NO2. That's another way that you may see this functional group. All right, so those are some common names. And if we go through the naming of our species, the most common naming practice that you'll see are using our carbon species. So looking at our alkenes, where we'll use the ENE ending to indicate that there's a carbon-carbon double bond present in our molecule. And if we're treating our double bond as a substituent, right? So if there's a double bond that's attached to a longer carbon chain, we'll add YL. And then we'll use YNE for our triple bond alkyne. And then enol. Our alkane are just our carbon single bonds will be ANE ending, and it'll be alkyl. And then for our ether, it's still an ane species. We'll talk more about those. But if it's a substituent, we'll call it an alkoxy group. And then for our halogen, we'll just have an ane. We'll add an O ending to our substituent. So fluoro, chloro, bromo should be the prefix. And then for our nitro, it should still probably be an ane, and then the substituent will be our nitro prefix, right? So that's kind of the functional groups that we want to identify. And the functional groups will determine the last part of our name. Whatever functional group we have present will determine the last part of the name of our organic molecule. What determines another part of naming our molecule is we need to actually look at how many carbons are present in our longest carbon chain. So for example, if we are looking at our longest carbon chain, if it has 1 carbon, we'll use the meth prefix. If it has 2 carbons, we'll use our F prefix. We can use prop for 3, but for 4, pent is 5, hex is 6, hep 7, oct is 8, non is 9, and dec is 10. Right? So these would be how many carbons are in the longest chain. So we'll go through some examples to kind of explain this a bit more. For exactly what I'm talking about. So we can also look at having other functional groups, right? So functional groups that are, other substituents, and these are just attachments to our longest carbon chain. That's what our substituents are. So we can have some that are a little bit different. And if we have a 3-carbon system, one that would be attaching so if we attach our parent chain, so we'll call that R, through the second carbon of a 3-carbon chain, this is called our isopropyl group. The systematic name for this would be 1-methyl ethyl. We can also have 4 carbons, which will be our butyl species, right? 4 carbons is our butyl species. So we can have isobutyl, where our parent chain is connected to basically a CH2, a carbon with 2 hydrogens, a carbon with 1 hydrogen, and then 2 methyls. Our sec butyl is our parent chain being attached to our second carbon in the 4-carbon chain. And then our tert butyl means that we have a carbon that has 3 other carbons attached to it. Right, so I actually want to draw that last one a little bit differently just to keep it consistent. So it should actually be, this would be a carbon, and then it has 3 other carbons attached. So that carbon actually has, the carbon highlighted here, has no hydrogens at all, right? So our tert butyl species is a tertiary carbon and has no hydrogens. Our sec butyl species is a secondary carbon and only has 1 hydrogen. Our isobutyl species is primary, so there are hydrogens next to our carbon, right? 2 hydrogens there. And then our isopropyl is, we'll consider that to be secondary as well because it has 1 hydrogen present, right? So what you've seen me switch in between in this first page of the workshop is our bond line structure, which we see below here. So this is the bond line structure where we're representing each carbon as a dot, right? So each carbon gets represented as a dot. And then we're going to connect those carbons with a line. And what we see above is the actual more of the Lewis structure. So this would be a complete Lewis structure if I added lone pairs to every atom that needed them. So oxygen should get lone pairs, nitrogen should get lone pairs. But it would be a complete Lewis structure if I put in the lone pairs there.